on Friday, we went over the Doppler effect, okay? And we said that the Doppler effect is a perceived change in the frequency of a wave, not the actual, because we know that obviously the frequency of a wave never changes once it's produced. But we might perceive it to be different because either we're moving into the waves and encountering them at a higher frequency than they were produced, or, for us, the source is moving, okay? And as it makes the waves, they don't get as far away as they should because the source is moving along with them and we hear a higher frequency. That's if the source is coming towards us. If the source is going away from us, then it produces a wave and runs away from it before it produces the next one, and we hear a lower frequency of sound. Even though the source is making the same frequency, we don't hear that because of the nature of the movement of the source. Everybody? Oh, okay. Now, the formula we went over is this one. The Doppler frequency, so this is the frequency that we perceive, hear, measure, whatever, okay, is equal to the actual or original frequency, okay, that is actually produced by the source, multiplied by the speed of the waves, divided by the speed of the waves plus or minus the speed of the source. Okay, how do we decide plus or minus?
Coming towards you or going away from you?
Right, if it's coming towards us or if it's going away. If it's coming towards us, then we subtract, okay? Because we want the observed frequency to be higher than the original frequency. That's why we want a smaller number on the bottom, why we subtract on the bottom, okay? If the source is approaching us, okay, then we're going to want f to be smaller than FO, so we're going to add on the bottom so that when we do this operation here, okay, we get a decimal, okay? We multiply by a decimal, we get a smaller number. Everybody all right with that? Okay. On Friday, we did one example of how to calculate F. We did one example of how to calculate FO. Okay, but we didn't get to an example of how to calculate VS. I showed you the manipulation, but we never did an example of it. Okay, so number 4 is an example of a question where you will have to calculate VS. So I'd like you guys to write that one down and see if you can do it, okay? And then I will go over it with you, okay? Just so that we get the hang of it. Then I'm going to have you guys work on some practice problems, like I say, for maybe another 20, 25 minutes. And then I'm going to pile through 2 exam review things really fast, especially the final one. That's going to have to be super fast, okay? Just so we can get through it all. All right, give number 4 a try. So in this question, okay, we said we're looking for VS in this question. So the givens are that the frequency of its whistle is determined to be, okay, 475 hertz. So I would say that's F. And we can confirm that in just a minute. Okay, the actual frequency of the whistle, confirmed. Okay, this is actually said the actual frequency of the whistle, so that's FO is 500 hertz. Here's where I was going to confirm it. Okay, I know it's approaching, or sorry, is moving away from me, so I know that this frequency should be lower than this one. Okay, all right. And the other thing they tell me is that the speed of sound in air, or the speed of the waves, is 350 meters per second. So I'm looking for VS. All right. In this particular one, because the object is retreating, I will be adding VS. Okay, so when I want to manipulate to solve for VS, the first thing I want to do is move FO over to the other side. So I'll have F over FO equals V over V plus VS. Now, what I want is on the bottom of the equation, and I can't solve for it there. I need it on the top. So what I'm going to do is reciprocate both sides. Okay, the rules of algebra allow me to do whatever I want to an equation, as long as I what? As long as I do it to both sides. Okay, so FO over F equals V plus VS over V. All right, now I can do further manipulations to get VS by itself. So I'm going to multiply both sides by V, and then I'm going to subtract V. So what I'll be left with is FOV over F minus V equals VS. Okay, it's a tricky manipulation. When we plug in our numbers then, we're going to have 500 times 350 divided by 475 minus 350. Okay, so when we punch all that in, we should end up with 18.4 meters per second. So in your calculator, right, 500 times 350 divided by 475 minus 350. Okay, 18.4 meters per second. Okay, like I said, that's as tricky as they're going to get. Okay? Solving for Vs is the trickiest manipulation. It's probably a little trickier if the object is approaching, okay? Because if it's approaching, you would actually have to get Vs on the other side first, so you're not solving for a negative number. Or you can leave it there and solve for a negative number and realize that it's not negative when you're done. It's up to you. Okay? Questions on that one? Okay. I'm going to have you guys working on some of the ones from your digital workbook here, and I'm going to tell you which ones I want you to do so you don't do too many, and we can get to our review for the exams. Okay, so you guys. Okay, I'm going to want you guys to do 1, 2, 6, and you're solving for actual one. I'll say 1, 2, 3, and 6. Okay, so give you some time to work on those 4. Okay, if there's questions, we'll go over them together, and then we'll move on to doing review. Okay. All right, so on number 3, okay, we're being asked how fast the source of the sound must be moving. So we're looking for Vs, okay? If the observed frequency is 3% higher than the true frequency, assume the speed of the waves is 340 meters per second. All right, so all I have to do here is pick any 2 numbers I want that are 3% different. I'm going to pick 100 and 103 because they're 3% different. Does that follow me there? That's sort of the trick to the question is I can pick any numbers I want as long as the difference is 3%. Okay, 200, 206, or 300 and 309, it wouldn't matter as long as they're 3% different. Okay? So I'm just going to say then that FO is 300 and sorry, I said 100. 100 and F is 103. So I'm saying an approaching object, but it wouldn't make any difference. Okay, so I am going to take FO, V over V minus VS. Okay, and then all I have to do is solve for VS. So I'm going to manipulate here. I'm going to divide both sides by FO, and then I'm going to reciprocate so that I've got V minus VS on the top over V. Multiply both sides by V. Then I'm going to add VS to both sides so that it becomes positive, and I'm not solving for a negative, and then I'm just going to subtract this over. So I'll have that VS equals V minus FOV over F. Okay, so that'll be 340 minus 100 times 340 divided by 103. Okay, so 340 minus in brackets 100 times 340 divided by 103. All right, so it must be moving at 9.9 meters per second. Okay? And it wouldn't matter which frequencies I chose or whether I chose approaching or retreating. A 3% change means 9.9 meters per second. Okay? Does that make sense, everybody? Okay? So the amount the frequency changes is only dependent on how fast the object's going, not whether it's approaching or retreating. Okay? I could have switched those two numbers and made the observed frequency be 100 and the actual frequency be 103. It's still got 9 points. All right, any other ones we need to go over? How many people have done all 6?
Can you go over number 2?
Number 2? Yep. Okay, so we've got Mark standing at a railway crossing in the way of the train, which is not smart. Okay, the train is approaching at 100 kilometers per hour. I almost automatically converted it to meters per second there. So the trick to this question is you have to convert the speed from kilometers per hour to meters per second. I can't use kilometers per hour in the formula. Okay, so the speed of my source is 27.7 meters per second. I think that's right. Divided by 3.6 is 27.7. Okay, it's sounding its whistle, which is 400 hertz. That's FO. Okay, to signal him to move. And the air temperature is 20 degrees Celsius. So I'm going to use that to get the speed of my waves. V equals 332 plus 0.6 times the temperature, which they told me is 20. Okay, so that's why they give you that, just so that you have to use this extra formula. Spoiler alert, I'm going to ask you to do exactly that on your unit exam tomorrow. Okay, so that's all you have to do. Punch it in like that. Speed of sound is 344 meters per second. Okay, so now I've got V, I've got VS, I've got FO. I'm just looking for F, which means I don't even have to manipulate the formula. I just have to plug in my numbers and understand that the train is approaching him. It would do no good for the train to warn him after it passes, because that would be tragic. Okay? That's also why you don't stand on the railroad tracks. Okay? A lot of people every year get killed by trains because they're on the railroad tracks wearing their headphones. Rule number 1, don't stand on the railroad tracks. Rule number 2, don't stand on the railroad tracks while wearing headphones. Rule number 3, don't stand on the railroad tracks. Yeah? Pretty simple stuff. All right, so 400 times 344 over 344 minus 27.7, okay? And that should give us our actual, or sorry, our perceived frequency. Okay, so the actual frequency of the horn there is 430, or sorry, the perceived frequency is 435 hertz, okay? Which makes sense, it should be higher than it's actually being produced at for that. Okay. All right. How many people have done number 6? Okay, I'm gonna give you just a couple more minutes to try number 6. Okay, and then we're going to move on to the review. All right, so we've got these people who are in the halftime show of a football game. Okay, they are cheering with a frequency of 784 hertz. So that would be our FO. Okay, they are moving towards the audience at a speed of 0.83 meters per second on a day when the speed of sound, whoops, sorry, I got to find this, where the speed of sound is 343 meters per second. What frequency does the audience hear? So again, we're looking for the Doppler shifted frequency F, which doesn't require us to have to manipulate the equation. Okay, so FO V over V minus VS, because these people are walking towards the crowd. Okay, so we've got our 784 times 343 over 343 minus 0.83. Is this going to make much difference? They're barely moving. Okay, 0.83 meters per second is like a crawl. It isn't going to Doppler shift your frequency very much. Okay, so we might be looking at maybe 1 or 2 hertz tops here. Okay, that we would see a change. So 784 times 343 divided by 343 minus 0.83. 786 hertz. Okay, you probably wouldn't even notice that. Okay, it's not like when an ambulance is coming towards you and you can clearly tell that the sound is being shifted. Okay, you're probably not going to notice 2 hertz. Okay, it would take someone whose ear is pretty finely tuned to notice that. So maybe if you were in the business of tuning musical instruments, you might be able to perceive that much of a change. Okay. All right, any other questions on the Doppler effect stuff? Okay, so let's talk about your unit exam here. So you might want to take out a sheet here to write a couple of things down. Okay, so remember that this unit actually still contains all the stuff we did before Christmas as well. All the stuff about simple harmonic motion, pendulums, masses on springs, conservation of mechanical energy in simple harmonic motion, okay, Hooke's law, that stuff. It's all part of this unit, but I know it feels like forever ago, okay, but that stuff is still on here. Okay. So the first thing that we went over in this unit was simple harmonic motion. There are going to be some multiple choice questions asking about your understanding of simple harmonic motion. These are going to be things that are going to ask stuff like, you know, what's the nature of the restoring force for an object moving with simple harmonic motion? And you're going to have to remember that it varies linearly with displacement, okay, in order for that to happen. Okay, remembering what kinds of things would affect the period of a pendulum, what kind of things would affect the period of a mass on the spring, okay, that kind of stuff, the recall kind of stuff is going to be tested in the multiple choice for sure. And there might be some very simple calculating in the multiple choice, but not very much. Okay, there's actually, those are 20. No, it's even less than that. I think it's like 15 multiple choice. Like it's a very short multiple choice section on this one. Okay, so just know the simple harmonic motion, and there's going to be some problem solving to do with a pendulum and a mass on the spring. There's one for each. Okay, there's a pendulum problem in the written, and there's a mass on the spring problem in the written. Okay, so there's one for each. So that would involve these formulas here. Period equals 2 pi times the square root of L over G. That's for the pendulum. Okay, and period equals 2 pi times the square root of M over K. That's for the mass on the spring, where M is the mass, K is the spring constant. Okay, and the other formula, L is the length of the pendulum, and G is the acceleration of gravity. Remember, those formulas are on your formula sheet. You don't have to memorize them. Okay, but there's a problem for each one of those. Okay, and then we talked about Hooke's law. Okay, remember the Hooke's law is about the restoring force varying linearly with displacement. So the force in a spring or any restoring force, okay, is going to be negative K, the stiffness of the spring, times X, the displacement from the resting or equilibrium position. So the greater X is, the greater F will be. Right? And F is always going to be in the opposite direction of X. That's why the negative is in that formula. So if I compress a spring by pushing it to my right, the spring is going to push to my left. Okay, and that's what the negative will make sure that we get in that kind of a problem. There is a Hooke's law problem in the written. Okay, now remember, the most common type of Hooke's law problem that we dealt with is where Hooke's law is being offset by gravity, just like Hooke's experiment. He hung all those springs from his ceiling and hung weights on them to see how far they would stretch. Okay, in a case like that, okay, the spring Fs is pulling against but is equal to the force of gravity hanging from it, right? It's not moving, it's just hanging there. So the net force is 0. That means gravity's pulling down, spring force is pulling up, and the net force is 0. Okay? So you could have a question like that that says he hangs like a 500-gram mass from a spring. Calculate X or calculate K if as long as they give you the other one. All right? Everybody with me there? Okay, and then we talked about conservation of energy for simple harmonic motion. Okay, and we said for a pendulum it's exactly the same as a roller coaster because it uses gravitational potential energy. But for a mass on a spring, it uses elastic potential energy. Okay, so when the object is oscillating back and forth, okay, it's constantly changing the elastic potential energy into kinetic energy. Okay, so if I'm looking at a couple of positions here, like let's say here's the point of maximum compression. This would be our equilibrium position. Okay, and that would be our point of maximum stretch. Okay, where does the object have the most elastic potential energy? Okay, which one? The third one and the first one, right? Okay, any point where it's either maximum stretch or maximum compression, okay, that's its amplitude, its point of maximum diversion from equilibrium, okay? So maximum EP, okay, maximum EP, okay, and remember we call this distance and this distance the amplitude, okay, and here at equilibrium, it would have kinetic energy only, which also means it's moving fastest there. How fast is it moving at the other two positions? Right, 0. Okay, because it's being slowed down by the spring until it instantaneously stops, and then the spring wins, and boom, back it goes towards equilibrium. Okay, same here. The spring is stretching, pulling back, stopping, and then winning. Pulling it, actually getting it to move back towards equilibrium. Okay? So, remember this. EI equals EF. Okay? And I made the conservation of energy question pretty simplistic. Okay? Like, it's not a point in the middle. Okay? And by in the middle, I mean like here. It would use this point, the equilibrium position, but not a position between equilibrium and max. Okay, so it's pretty straightforward. All right, so yeah, look, there's one of those on the test. In case you didn't get that from my previous statement, there's definitely one of those, okay, on your unit exam. Okay, and there's also a couple of multiple choice questions about energy in simple harmonic motion. Okay, and that was it. That was what we did before Christmas. Okay, then as soon as we got back, we had 5 days to go through waves, which is fast, okay, but we're good. Okay, so properties of waves. Make sure you know things like period, wavelength, amplitude, okay, you know, what a wavelength looks like, what a complete oscillation looks like, that kind of stuff is going to be in the multiple choice, terminology checking, okay, things like that. You know, what properties go with what wave form. So, as an example, if I'm looking at light that's really, really bright, okay, that has to do with its amplitude. Okay, really, really bright light has a very high amplitude, okay, but a very, very short wavelength, right? Very quiet sounds have a very small amplitude. Okay, because the loudness and the brightness have to do with the energy of the wave, not the speed of it. Okay, everybody with me on that? So there could be some questions that ask, what property of waves deals with this? All right. Also remember things like, you know, a wave is a traveling disturbance. A wave requires a medium in which to propagate. Okay, that kind of stuff. A wave is not matter. Okay, all of that kind of stuff is going to be properties of waves, multiple choice stuff. Okay, universal wave equation. Universal wave equation is involved in all but one of the wave problems. Okay, because after all, it's universal. Okay? It's a pretty important part of basically everything we do in waves. So it's really only not part of the Doppler question. Okay? Everything else it's going to be a part of if we're talking about waves. Okay? When we talked about the universal wave equation, we talked about echo questions. Okay, so if you shout at a cliff, right, the sound goes there and back again. So you can use V equals D over T along with, okay, along with that. Also remember the other manipulation of this because it's not on your formula sheet. Okay, because T equals 1 over F and F equals 1 over T, these two things mean the same thing. Could have a question that involves, you know, like an echo and then a calculate a wavelength or calculate a period or something like that kind of question. Okay. The other thing we talked about with the universal wave equation was, and this kind of goes with wave properties, if a question says 10 crests go by, how many waves went by? 9. Okay, remember we start counting with the first visible waveform, that would be the crest, so that's 0. Okay, and then we have 10 crests counting 0, that's actually only 9 waves. Okay. All right, then interference. All right, I already told you that what I'm going to do on the test is I'm going to put 2 waves on a piece of graph paper overlapping, and you have to tell me what kind of interference is occurring, constructive or destructive, and draw the resulting waveform based on the law of superposition. Okay, so were I to give you, let's say, this wave and that wave, would I be looking at constructive or destructive interference? This is constructive. They are in phase. When one is up, the other is also up. When one is down, the other is also down. What do we do with their amplitudes? I put them together, right? Okay, so the resulting amplitude of this wave would be the sum of the amplitudes. The sum is important, okay? That's why I'm putting it on a piece of graph paper, so you'll know this wave's amplitude is +3 and this wave's amplitude is -2, or whatever it happens to be, so that you can draw the actual waveform in the right place. That would be important. All right, so is that a gimme question? That's a gimme question. Okay, it's 3 marks and they're gimme marks, so make sure you get that one. Okay, waves at a boundary. There's some multiple choice questions about this. What do waves do when they encounter a boundary between 2 media? Well, their speed changes, their wavelength changes, the frequency stays the same. All right, and at any boundary, some wave energy gets reflected and some gets transmitted. So I'm going to give you pictures before and after and ask you, is the second medium more or less dense than the first? Or is the second medium slower than the first? You got to base that on, okay, what does the transmitted wave look like? What does the reflected wave look like? Okay, if we hit a more dense medium, then we're going to slow down, get shorter, and have what kind of reflected wave? Upright or inverted? Inverted. Okay, that you just have to memorize. So you got to go back in your notes and go over wave behavior to boundary and memorize. All right, if it's an inverted reflection, it was more dense and slower. Okay, if it was, you know, an upright wave, then it was less dense and faster. Okay, that kind of stuff. So make sure you know that. Okay, so there's no like problem solving to do with that. It's all diagrams and being able to discern what's more and less dense. All right, standing waves. These are air column questions. Okay, so you've got 2 kinds of air columns, open and closed. Okay, open air columns, right? When they resonate at their fundamental frequency, we get that waveform inside, which means that the length of the tube, okay, is half the length of the waves, because there's half a wavelength in the tube. Okay? If we're dealing with a closed air column, when it resonates at its fundamental frequency, we get this waveform inside. Okay? And that means that's how much of a wavelength there. 1/4. So lambda equals 4 times the length of the tube for a closed air column at its fundamental frequency. And the question is asking about the fundamental frequency. Now, something you need to remember about closed air columns. Okay? Closed air columns only resonate, that is, make sound at odd frequencies. Okay? This is what F1 looks like. F2 looks like that. What's at the top? What do we call that point of total destructive interference? A node, right? Terminology, okay? You gotta know that. That's probably in the multiple choice, probably, definitely. Okay? So make sure you know your antinodes and nodes. That terminology is important. There's a node at the top. So while there's a wave here, there's no sound. Okay? It doesn't make any noise at F2, but it does make noise again at F3, okay, when we've got that happening. Okay? Other thing we have to remember, F2 is twice F1. F3 is 3 times F1. F4 is 4 times F1. Okay? It's factored really. Everybody good with that? Okay? That's how you make musical octaves on an instrument. Okay? Like if you're looking at all the strings in a piano, okay, they're related by their length and the frequency they produce. So one C after another is always the same ratio difference. All right, so standing waves, air columns, same thing, okay? There's, like, again, terminology stuff about standing waves in the multiple choice, okay? But beyond that, the only standing wave question in the problem solving is an air column question. So make sure you know how to do those. And I'll even go as far as to tell you it is a closed air column. You're welcome. Okay, and then the last thing is what we did today, Doppler effect. There's a couple of Doppler effect questions in multiple choice, basically just asking your understanding. So, you know, if an object was approaching you, what frequency would you hear? Louder, quieter, more higher pitch, lower pitch, and you would have to pick, okay, the right answer. Okay, and understanding what the Doppler effect is. There's a multiple choice question about exactly what the Doppler effect is. Okay, so just make sure you go over your notes. There's not that much to read on the Doppler effect. And then there's one problem in the written. Okay. And the problem in the written, it's going to ask you to solve for the speed of the source. Really focus your studying by studying that manipulation of the formula. Okay. All right, questions there? Okay, now I gotta quickly talk about the final. Okay, the final exam. What's on it? Everything. But don't worry, that's not where I was going to stop. Okay. So on the final exam, there are, I want to say 21 or 22 multiple choice questions. Okay, they are like either incredibly simple calculations, like v equals d over t, or interpret this graph, like really simple stuff. Okay, that's basically all that's in the multiple choice. Or if it's something that has to do with diagrams, like some of the stuff to do with waves, okay, it could be in there with diagrams. But the multiple choice is a very short portion of the final exam. Okay, for the final exam, I just want to make sure I get this right. I'm just going to open it up and tell you. Okay, so you might want to write this down. Okay, 21 multiple choice questions. And they're arranged generally by unit. Okay, so the test generally goes by unit. I say generally because there's some concepts that overlap, and so you could have a question that's kind of two units together. Okay. But yeah, there's actually quite a bit in the multiple choice on waves and simple harmonic motion, like half of the multiple choice are waves and simple harmonic motion questions. So simple recall stuff. Okay, so in Unit 1, kinematics. Okay, the things we went over in kinematics that were really important: graphing, vector addition, acceleration, and projectile motion. Now, the best way for me to assess all of that stuff is to use a projectile motion question, because it requires you to do acceleration calculations, it requires you to do vector components, it requires you to do v equals d over t. Okay? So, the first question in the written response is a projectile motion question. And it is just like so many of the ones we did in class. Okay? Projected at an angle, projectile motion problem. Okay? You're going to be asked to do the same things you were asked to do in class. Calculate how long it's going to be in the air and how far it's going to go at its maximum height. Okay? That's what you'll be asked to do. Okay, and then there is a graphing question. Okay, we only went over two kinds of graphs: position versus time and velocity versus time. Okay, this one is going to require you to do a little interpretation and a little calculation from the graph. Okay, question number 3, gravitational field strength. Okay, so it's just a problem about gravitational field strength. You got to do a little bit of calculating there. Okay, and then question number 4 is probably the toughest one on the test. Okay, it's a Newton's second law question. My favorite kind, which is inclined planes, but it's also a system. Okay, so it's an inclined plane that's a system. So it involves a pulley. What do we do with the masses in a system question? We put them together. Okay, remember, whatever forces are acting in a system, when you get the net force, whatever it is, acts on the entire mass of the system. Okay? So you can use the individual masses to figure out the individual forces. But when you get to the end, and you're dealing with the net force and the acceleration of the whole system, spoiler alert, that's what you're going to be asked to calculate, okay, you need to use the mass of the system. Okay, question number 5 is a law of conservation of energy question. Involving a roller coaster. question number 6 is a vertical circular motion question, also involving a roller coaster. Number 7 is a satellite motion question. Doppler. Nine, open air columns. So you got a closed one on your unit exam, you got an open one on the final. Question 10, unbanked curve.
What are you talking about?
No, I don't like that.
Okay, what keeps you in an unbanked curve? Friction. Okay, FC equals FF. All right. Number 11 is vector addition with Newton's second law. So something's being pulled by two forces. We need to find the acceleration. Okay, so you got a vector addition to get net force and then find the acceleration. And the last question is a Newton's second law friction question. The context of that question is a car slams on its brakes. You will be asked to calculate the coefficient of friction. Okay, why am I giving you so much detail on your 2 exams? Don't say it's because I'm a nice guy, because I'm not. Okay,
That's all wrong.
it's not all wrong. Okay, no, I'm not trying to. I'm not trying to pull wool over your eyes. I'm not trying to trick you or anything like that.
Everything you said isn't on the test.
No,
The test is nothing.
no. This is what your test is. The reason I'm doing this is because you lost a week of school where you could have come in and asked for help. We lost that time, and now we can't do a final exam review, where I would have just gone over examples like these. Okay, I wouldn't have said this is on the test, that is on the test. I'd have just gone over some random examples that were like the ones that were going to be on the test. Which, by the way, you can see if you watch any of the podcasts I posted for final exam review. Okay, so here's what I want you to do with what I've given you today. Do those types of problems. Focus your studying. Okay, now you can really go, okay, I know I don't need to do a projectile motion question about a car driving off a cliff horizontally, because Mr. Coder said specifically the question is about a projected at an angle projectile. I need to do those kinds of questions. Okay, and I told you specifically I'm going to ask for time in the air, distance traveled, maximum height. Do questions where you're asked to do that. Okay, you've got a bunch in your digital workbook with the answers. Okay, so you can check them as you go. Right, and you've got the ability to go back and watch the podcasts of me doing questions just like that if you need to watch them. Okay, so that's why I'm telling you this much detail. So you can go, all right, I know I need to show Mr. Coder this. I need to study this. You don't have to now worry about wasting your time studying things that aren't going to be on the exam. Okay, so focus your efforts on the things I've told you aren't going to be on there. They are what's going to be on there, right? That can help you save a little bit of time. Because I would imagine if I were you, I would feel a bit rushed and feel like things are snowballing. Okay, so I'm trying to help you out by saying study these specific things. Okay. So your exam, guys, remember, is the 24th at 9 a.m. It's in this room. Okay, so come here, and the desks will be sideways like this. Okay, your tests will be laid out alphabetically. A in that corner by the pencil sharpener, and then they'll go down that row, down the next row, down the next row, alphabetical order. Find yours, sit there. Okay, I'm going to come around and I'm going to clear your calculators. Right, so before the final exam, we blank the memory in your calculator. So if for some reason you're storing something in the memory of your calculator, you best offload that before you write an exam because it will be clear. Okay. Don't bring your formula sheet. You're getting a fresh one. Okay. The last page of the test is the formula sheet. Just rip it off. Okay, and you can have it out and use it. Okay, it's exactly the same as the one you have, minus whatever you've written on yours. Okay. So you're getting a fresh one of those. Bring to the test, obviously, your calculator, some pencils. Okay, I wouldn't recommend even bringing a pen. Okay, bring several pencils so that you can erase and stuff like that. The format of the test is just like a unit exam, it's just longer. Okay, there's some multiple choice and there's some written response, just like a unit exam. If you need to, bring like a bottle of water or something to drink. And if you can't go 2 hours without eating something, bring an exam appropriate snack. Okay, what I mean by that is not something really smelly, not something really noisy. Okay, because I've seen both, and they're really distracting to others. Okay, so what we want here is be considerate of others. Bring something like a granola bar. Okay, yes, it'll make a little bit of noise when you open the wrapper, but it's pretty minor. Okay, like don't bring a big grapefruit. Okay, because your hands are going to get all sticky when you peel it, and if it's a good one, the whole room will smell like grapefruit. Which I don't mind, but other people might find distracting. Okay, because we had one kid who came into a final exam with a 4-course meal. Okay, he had like a roasted chicken from Sobeys with mashed potatoes and vegetables. Okay, I don't know when he was going to write the test, but he had like a full meal that he brought with him. But the whole gym smelled like roast chicken. Okay, which not bad smell, I like chicken, but it's distracting if you're trying to write a test. Okay, so just be considerate of everybody else and make sure that if you're going to need to eat something that it's not going to bother others. Okay, while you're eating it. Okay, yeah, that's really it. Your phones will obviously have to be surrendered at both the unit and final exams, turned off completely so they can't transmit. Okay, smart watch or anything like that also will have to be surrendered. Anything that's capable of sending and receiving has to be turned off and put in the box and back at the end. Okay, or just leave them in your locker if you had a locker. Probably not many of you did. So, yeah, just know that stuff will happen. You have to stay in the final exam for 1 hour. Okay, if you're done this exam in 1 hour, you are either destined for greatness or you didn't do very well, and there's really no in between on that. Okay, I have had very few people who were done in an hour who did well. I'm not throwing down the gauntlet of challenge on that one. Okay, I'm just telling you that as a fact. Okay, because I had a kid who did take that as a challenge, and after an hour he handed in his test, and it was like 2/3 done. He's like, "I'm done. See?" I'm like, "You failed. See?" Okay, yeah. So don't do that. Yeah, but he was done fast, and yeah, so was his 5 credits. So we don't want to do that. Take your time. Okay, it's a 2-hour test. It should take you about an hour and a half to an hour and 40 minutes if you manage your time. Okay, and that'll give you time to look it over and all of that kind of stuff. Make sure you show up about 15 minutes early. Okay, we generally let you into the room at about 10 to 9. Okay, so you can find your test and get situated. Usually you're starting a few minutes early. Okay, so you get a couple extra minutes at the beginning, but know that at the end of the exam is over. Okay, after 2 hours, we're going to come and take your test. So you have to make sure that you're done. It's really awkward when I'm fighting with you and it tears in half. Okay, so just make sure that you're managing your time and you're done. Okay, at the end of the 2 hours. I can't think of anything else I got to tell you about the final exam. Oh, obviously, reminder that we've decided that it will be no fault, but can replace your entire course mark. Okay, so if you got 83 right now and you get 87, you got 87 in the course. Okay, that's our incentive for you to study hard. Okay, you can't do worse, but you can sure as hell do better. Okay, that's kind of a big deal, especially if you're sitting at a 65 and suddenly you pull off a brainiac performance and get a 92. I've never seen that happen. But okay, if it did, holy crap, good on you. Okay, I'll give you a 92. Well, I mean, if you can get 92 on the final exam, then you knew 92% of the material. That's a pretty sweet deal. Okay. So just know that that's what Mr. Dickey and myself have decided we'll do. So his class is getting the same treatment. So there's no advantage being in my class or his class, except that he's a better teacher, so you're at a disadvantage. But, okay, and then for your unit exam tomorrow, okay, same deal. Make sure you got stuff to write with. Okay. Did I post the review? I did, right, for the unit exam? Yeah. Okay. It's a pretty thick booklet. I don't know why that one is so big. Okay, but there's a bunch of questions in that you don't have to do. Actually, let's have a quick look at those, just so you know which ones you don't have to do. I had it in here.
Yeah, I know. I'm just
Okay, so for this, guys, so all this stuff here on the first page, okay, this fill in the blank stuff, the stuff about nodal lines, no, I took it out, never mind, it was question number 9, I took it out already, okay, so there's a key for the fill in the blanks, okay, so those are, any ones that are left on there, you can do just fine, and a lot of this has to do with some of the multiple choice that will be on the exam. Okay. When it comes to the problem solving, some of these are pretty simplistic, okay, and these are not the types of diagrams you're going to get on your unit exam. Okay, they're just some questions that I was able to find. These ones are good. The Hooke's law question is fine. The energy and simple harmonic motion one's fine. There's one in here about beat frequency or something, right? Or did I take it out too? Maybe I was really on the ball. I was really on the ball. I did take it out. Okay. Yeah, so yeah, you can do all of those. And this is the key here at the end for some of the other pages. So there's a fill in the blank key, then there's this key for the other questions. And then, yeah, for the ones that I made, the answers are here. These are the answers. Okay, so this 4 here that's all by itself, that's for the question I took out. The answer is 4. I have no idea what the question was, but you'd never do it. Okay. Yeah, so you're good there. Okay, to do those, there's some of each type, but obviously you know what to focus on because I told you exactly what will be on there. All right. It's been fun. I won't be able to talk to you guys much tomorrow because you'll be writing through exam tomorrow. Okay. So just make sure, guys, if you have questions during exam week, you can email me. I'll do my best to help you out. If I've really got time, we might even be able to set up like a Google Meet as long as I have access to my classroom. Okay, which is not often, unfortunately, during exams. My classroom is being used to write tests quite a bit, so. I might get back to you and say, can you talk at this time, and then we can open up the Google Meets and do it that way. Okay. but we'll kind of see how that goes. Okay, so I apologize for the time crunch, even though it's not my fault. It's not my fault. Okay. All right. Let's get you guys packed up so I can come around and wipe down your desks.